Welcome back. Another divergence from the regular scheduled videos that you've been watching. This is the part 2 of the linear actuator install, but there's a reason why this is going to be different. It's because, well, I lost 3 months worth of video recording in memory card failures, and so I'm kind of piecing things together. So with that in mind, let's carry on and see this. This is the linear actuator now installed on the Challenger 2. And you notice there's no little lever that converts 2 inches to 1 inch. It's directly connected to the linear actuator, and I bolted the linear actuator straight down onto that bar at the top. And there's a reason for that. Hey, let's take a look at the other side. There we go. Oh, no, actually, that's the still picture I took. Okay, so this is what it looks like. This is now its permanent position. It is wired up and it is fully functional now. At least it is in this video. And I'm trying to keep the camera angles when I took these pictures very recently, like today, to keep you from seeing other things that are way far down the line in progress that you haven't seen in the videos yet on how I made them. So sneaky me. Yeah, so this is what we're looking at here, and what I did was I modified the linear actuator. I discovered that rod only needs to move forward and back exactly 1 inch, not 1 1/4 that I thought. I was wrong. I measured it several times, and it was exactly 1 inch. So I took the linear actuator apart. Sorry, guys, at the manufacturing company, Progressive. And I relocated the micro switches that turn the linear actuator off when it reaches a stop limit. I moved the forward stop limit linear actuator micro switch back to the point where it stops now at exactly 1 inch throw. So now it's limited to moving forward and back exactly 1 inch, which is exactly how much it needs to move for this aircraft to move the flaperons. So that's what I did. No levers, none of that kind of stuff. It's a direct connect and a modification. I don't recommend you do this. I recommend you, when you order this, that you talk to the manufacturer at Progressive Automations and you have them build it for you. That way, it's a lot better, and it'll have warranty, because this one now no longer has warranty. So here we go. I'm going to show you it in operation, and watch this. There she goes out, and there she goes in. Wow, cool. This is the control box that is moving the linear actuator, which is triggered by the new hand grip I've got on my joystick. This control box fires 3 relays, actually. 2 relays that are tied together to reverse the voltage to the linear actuator, so it moves in and out, and a 3rd relay for the push to talk. Now, what I've done here is I've included the build of that circuit board, and that's coming up in about 5 seconds. So I'm going to stop talking, and you'll see what I built to make all this work. Well, hello everybody. Not at the hangar, as you can tell. Welcome to another episode of Peter's working on his airplane. And again, I'm working on my airplane here. Well, I finally got the circuit boards in that I ordered. And these are going to end up being the... hang on. There we go. That's the back side. That's the front side. See how that turned out. Yeah, it turned out good. These are going to be the control relays for the linear actuator that moves my flaperons down, and is also the trim on the Challenger 2. And it's also the push to talk for the radio. Because the joystick handle that I got has the hi-hat for the
flaperons, forward and back, and the push-to-talk button, they all share a common. So it'll be a common ground. So when you push the push-to-talk, it'll short to the common, and likewise the flaperons up and down. I decided that I was going to isolate everything by making a little relay box to feed the push-to-talk through as well, rather than just feeding the ground right into the radio, just in case something happens with the switch gets wet. You don't want to send current through. Anyways, long story short, yeah, this is going to have 3 micro relays on it. It is the 4th or 5th design of this. I think it's maybe the 6th. I've gone through a lot of changes. Here's one. That was the latest one that worked, but had a problem. That for whatever reason, when I'm sitting down in front of the computer designing the circuitry, I just didn't think about it. And the problem with this one is only one thing. The power that's going into these 2 relays, the 2 big black relays here, that will move the linear actuator in or out, is variable, so that I can speed up or slow down how fast that linear actuator works. So if I want flaps, I've got a full speed, hit the button, flaps go down quickly or up quickly. Whereas if I just want trim, I turn the speed right down so I can hold the button and gently trim the aircraft. So, because it's variable, I made a mistake that I was using that input as well as to drive the transistors that feed the relays, and these are 12 volt relays. The coils are 12 volts, and yeah, it's just like, oh, why did I not even think of, that's what happens when you do design work at 2 o'clock in the morning, and you think you got it, and you say, okay, go click send, here's my PayPal, get me some circuit boards, I'm done. And then when I put them together and I started testing it, I'm going, oops, why didn't I think of that? Well, I didn't think of it because it was 2 o'clock in the morning. So I fixed that, and a couple other things with this iteration. I'm not using these big black relays anymore. These 12 amp switching is a lot. Because the maximum current draw on those linear actuators, at the highest they ever draw, was 1.5 amps. So instead I am using micro relays that have a 5 amp rating. More than enough. It's almost triple, well, it is triple of what the linear actuators will draw. And I also changed a few other things. I got away from my transistorized switching and everything else, and yeah, I went to logic circuit using a couple of AND gates and inverting gates and what have you, and which meant everything had to be logic level over 5 volts, which means now I had to put a voltage regulator on here to drop the 12 volt rail coming in from the aircraft down to 5 volts, give myself a 5 volt rail I can use to operate everything with, and then just switch the current that comes in and out to the linear actuator, completely isolated 100% from anything on the circuitry. All it does is it takes a current in, current goes out, and to the linear actuator, the voltage or current that operates all the components is on a separate 12 volt rail that is always 12 volts, and it still has the radio push to talk on there as well. So yeah, that's the redesign. So what I'm going to do today is I'm going to be putting solder paste on here, mounting the components, and baking it. You've seen that before. So I'll probably just speed up the video really fast. I'm going to move this camera closer, and hopefully you can get a nice close look at what I'm doing with it, if you're interested in that. If not, well, just skip through this video, because that's all this video is an update of me building this. Well, I did a little differently than the other boards that I've done. This little box, project box, it's a Hammond box that you can mount the circuit boards on here. It has little black standoffs, 4 of them, for circuit boards. I've never utilized those before. I just glued the boards down or put in my own standoff. So this time when I designed the circuit board, you'll notice it's got 4 large holes in it. And those large holes line up exactly with those 4 standoffs. So now the circuit board will just bolt right to it, and Bob's your uncle. So yeah, a little change from the previous designs, that kind of stuff. So yeah, that's the project for today. Hopefully you find it interesting and exciting and informative. And you've probably seen, like I said, this before when I built some of the other stuff. But hey, I have no idea what people like to watch, so I'll just keep making these videos. As it sits right now, I'm so way behind on editing the videos. I'm right now, as I'm building this, in the timeline where I've got a lot of stuff, the panels finished, that kind of stuff. I'm just right now uploading video number 1 when I actually bought the airplane, and before it was washed, and I'm just testing the fabric, and I haven't really got a clue what the hell I'm doing with it. Pardon the language. So yeah, I'm way behind on that. So I decided I better start getting editing and get this thing uploaded, and we'll take it from there. So anyways, follow along. This is going to be a simple build video. I'll try to keep it short. And if you have questions, put them down in the comments. I will try my darnest to read all the questions that you have and answer them as best I possibly can. So thanks for watching, and let's get at her.
Okay, here starts some of the narration of what is going on. First off, right there I'm squeezing a little bit of the solder paste out of the syringe because the tip might dry out a little dry chunks, so I just get rid of that. And now I'm placing tiny droplets of solder on all the tiny little pads that the components go onto. Now, just as a note, this video here was recorded well later on, months later, and I had recorded other videos in my workshop building other things, as you may have heard the reference that here we are again. So this video is out of sync from where I thought I was going to put it in, but the reason it's out of sync is because I lost almost 2.5 to 3 months worth of video recording in bad memory cards that I had purchased, and these memory cards, well, they just crapped out, and I lost countless hours. Probably close to 60 hours of video is down the drain, never to be seen again. So I'm trying to make up for it a little bit here and there, and doing the best I can. So you saw I was putting solder paste on all of the pads where components go to, and now I am grabbing the components and doling out the amount that I'm going to require for this job. So many of this type of resistors, so many of these kind of components, so on and so forth. And that white sheet of paper at the top there is actually the pictorial. It's not a schematic, it's a pictorial layout of the circuit board from the program that I use. And it tells me what value of component I chose to put where, and the orientation of the EPROMs and so on. Now, as I mentioned, I'm using logic gates for this particular one. I was originally using just transistors and then using the relays and back and forth. And the reason I'm using logic gates and they're ANDing gates with inversion gates, and I won't get too technical, but I want to make absolutely 100% sure that both relays that control a linear actuator never fire at the same time, because if they do, what will happen is a very big short circuit across my entire power supply, and I can start smoking things out. So it's one relay or the other, and it's a first past the post type of deal, where the first relay that is actuated, well, the first logic gate that closes inhibits the other section of the logic gate system from being able to be closed. It just simply can't happen. Now, I have also incorporated some fusing in here as well, so if they do both go, the fuse will, of course, pop. And then there's fuse on my panel that can pop. But I don't want to practice that. I want to make sure. So, yeah, the logic gates are what's controlling everything inside here, and it just took a little while to design that circuit, and then design the circuit board, and then send away the Gerber. It's called Gerber files to a manufacturer who will make these printed circuit boards for me, in exact dimensions, and silk screening, the whole works, and then I get them in, and I continue on by populating them with components. Now, as you can see here, I'm using tiny tweezers, and I'm putting the components on with tweezers. Well, you might be used to people working with electronics, and they're sticking the wires through the holes. Where there are no holes in this, other than the mounting holes. There are, and of course, holes for the wires. The components don't have holes. They are surface mount. And I'm using what's known as an 0805 package for the majority of the resistors and capacitors and what have you, and the transistors I'm using, and everything is a larger version of the surface mount, or SMD, components. And the only reason I did that is because of the human factor. I got to work with it. I can work down to the 0204 package, which is, or actually even smaller, and or is it 0402? Whatever. I can work down there and be very successful at it, but I didn't need to make the circuit board that small. And the reason I use surface mount when I'm working on these things is because I need to make the circuit boards as small as possible. If I used what's called through the hole technology, this board would be about 2 to 2.5 times larger, and I didn't want that. I wanted something small. It'll handle the current. Those relays are more than capable of handling whatever current I put through, and I'm feeding it 12 volts, and yeah, there we go. So that's the little bit of narration. I'm going to be coming up to a bit of a transition here, and I'll let you follow along that way. Okay, now here we see my Reflow oven. It's a toaster oven that was modified with a kit that I purchased, and I purchased the toaster oven. It was from Amazon, and it was a used or returned, refurbished, whatever they want to call it, and so it was really cheap. I paid like $35 for this toaster oven, but it was modified. An extra heating element was installed, and it's all computer controlled. There's thermostat or thermometers inside that pick up the temperature and control it, and there I go. I told it to reflow, and what it's doing now is it's pre-soaking. And there goes the transition. Now, if you notice, the display is now showing that the temperature is rising and is climbing up to the point where the solder is melting. It holds it at that temperature for about 10 seconds at the 220 degrees Celsius mark. And then when it's happy, it says, okay, time to cool down. A little motor turns, and you will see, if you watch closely now, there we go. There's the door opening. And that is starting the cooling cycle. I leave it alone until it goes below 100 degrees, and when it goes below 100 degrees, I can then open up the door fully and inspect the circuit board, which I will be doing in a moment. So there you go. That's called a Reflow oven, and they work beautifully. Man, my work has gotten a lot better since I built that.
Well, let's see what cookies got baked. Let's check and see if I messed up. It's still very hot.
Yeah, it's still hot enough to, well, maybe not burn me, but hot enough to hurt. So what I'm doing right now, which I've edited greatly, is I spend about 10 minutes looking at every single component, every solder connection, make sure everything is good. Now I'm going to post a little picture here of what the circuit board looks like when it's finished, and there it is. Look at that. That's what the circuit board looks like. Well, sort of. I made one more change and I redesigned it again because I wasn't happy with this layout. And the circuit boards are cheap, so I ordered 5 more boards, prototype boards, and redid it. But here in the next picture, we'll show you the size of components. And there we go. That's a resistor on the bottom and a transistor on the top, and that is the size of components I'm working with. Cool, eh? Well, now back to the regularly scheduled programming. And here is the controller, the joystick controller. Moving the linear actuator one way, and now the other. Cool. And that's the push to talk at the front. That's the new hand grip. And of course it gets tied into this controller as we've seen before, and that's where the little circuit board resides, is in that controller. And yeah, that's it. That's how the linear actuator works. It's been a weird video, but I hope you enjoyed it. Thanks for following along. I do appreciate it. Yeah, these are the end credits. Like, subscribe, leave a comment, and ring that bell. And yeah, thanks for following along. I really appreciate it. Bye-bye.